In this video, I will illustrate with two examples how to use the ratio test to determine whether a series is convergent or divergent. As a quick reminder, here is what the theorem says. I have a series, sum of an, that I want to test for convergence. I'm going to compute this limit in blue, is the limit of one term of the series divided by the previous one in absolute value as n goes to infinity. I assume it either exists or is infinity, this limit, and then, if the limit is smaller than 1, then I can conclude the series is absolutely convergent. If the limit is 1, then the theorem doesn't help me, doesn't tell me what the series is, and if the limit is greater than 1, then the theorem tells me that the series is divergent. If you want a slower explanation of this theorem or a justification for why it works, I invite you to rewatch the previous video. In this video, I'm now going to try to use the theorem to test these two series for convergence. If you haven't done it yet, I invite you to pause the video, perform the calculations, see which conclusion you draw, and then keep watching. For the first example, I'm studying this ugly looking series, the sum over n of minus 1 to the n e to the 2n over n factorial n plus 3. I want to know whether it is convergent. I'm going to try to use the ratio test. For simplicity, I'm going to denote an, the whole term I am adding. According to the ratio test, what I need to do is compute the limit as n approaches infinity of the n plus first term over the nth term in absolute values. So I will start by simply copying that, and I just write the n plus first term at the top and the nth term at the bottom. Notice that I got rid of the minus ones because I have absolute values. And when having an expression like this, it's often convenient to group like terms with like terms. So I'm going to separate the exponential terms, e to the 2n plus 2 over e to the 2n, and the factorial terms, n factorial over n plus 1 factorial, and the polynomials. And now after doing that, those terms simplify a little bit, because e to the 2n plus 2 over e to the 2n gives me e squared at the top, n factorial over n plus 1 factorial gives me n plus 1 at the bottom, and I'll leave the polynomials as they are. And now I get here to this limit, and it's a polynomial of degree 1 at the top, and a polynomial of degree 2 at the bottom. So we know the answer is going to be 0. If you need it, factor the biggest term, or use L'Hopital, or you directly know it looking at the degree of the polynomials. Either way, the limit is 0, and since 0 is less than 1, according to the ratio test, the original series converges absolutely. So the series look complicated, but the calculation in the ratio test wasn't that bad. And in general, for any series that have terms like these with factorials and exponentials, the ratio test is a very nice tool to use because the calculation we have to do simplifies those terms. For the second example, I want to study the sum over n of n plus 1 over n squared plus 2. I want to try to use the ratio test to determine whether it is convergent or divergent. Like before, I'm going to call an the terms I am adding, and I need to compute this limit, an plus 1 over an in absolute values as n goes to infinity. I don't worry about the absolute values because the terms are positive, so here it is the n plus first term over the nth term. It's a quotient of quotients of polynomials. Let me reduce to a single fraction, and now compute this limit any way you want. Use L'Hopital, or factor out the biggest term, or simply notice it's a degree 3 polynomial over a degree 3 polynomial, so the only thing that matters is the leading coefficient, and the answer is 1. We got 1. For the ratio test, that's bad news. That means that the ratio test is inconclusive. This series is definitely convergent or divergent, but I don't know which one yet. The ratio test will not help me. Luckily, there is a different test that works much better for this series. Since it's a quotient of polynomials, it's perfect to use the limit comparison test. We can compare this series with the sum of 1 over n, and we will determine that it is divergent. And in general, whenever I have a series that is adding rational functions, quotients of polynomials, the same thing will happen. If we try to use the ratio test, we will always get limit 1, it will be inconclusive. But for all those series, when the term is a quotient of polynomials, then the limit comparison test is perfect, and it will help us compare it with a p-series that we know is convergent or divergent. In summary, the ratio test works very nicely for series with terms that contain factorials and exponentials, but works poorly for series with terms that are just quotients of polynomials. But for those series, the limit comparison test is perfect. So the ratio test and the limit comparison test complement each other very nicely.